In May of 1944, a geophysicist named Maurice Ewing stepped onto the deck of a research vessel drifting off the coast of the Bahamas. He was holding a seemingly insignificant device, a small metal cylinder containing just 4 pounds of TNT. Ewing had calculated that if he dropped the charge into the deep ocean and allowed a pressure fuse to detonate it thousands of feet below the surface, something extraordinary would happen. 3,200 miles away, off the western coast of Africa, another team of scientists was listening through a crude underwater microphone submerged deep into the Atlantic. When the TNT detonated, it created a sharp acoustic shock wave underwater. Ewing waited. Hours passed. And then, on the other side of the ocean, recording stations in Africa detected the blast. Somehow, the energy from just 4 pounds of explosives produced a signal that was still clearly detectable after crossing an entire ocean. Ewing had stumbled onto something big. But just like the early pioneers of stealth aircraft, the mathematics and physics of his era weren't fully prepared to explain what he had just witnessed. By the 1950s, as the Cold War was starting to heat up, the Soviet Union was building diesel-electric and nuclear submarines at a rapid pace. For the U.S. Navy, tracking them became a growing priority. The challenge was obvious. Submarines could disappear beneath thousands of feet of water. Years later, a small team of physicists at the Woods Hole Oceanographic Institution revisited Ewing's wartime research. As they worked through the physics of how sound travels under extreme pressure, they realized his results weren't a fluke. He had identified a layer in the ocean where sound could become trapped and travel extraordinary distances with very little loss of energy. The U.S. Navy quickly recognized what that could mean for submarine detection. The research was classified, and work soon began on Project SOSUS, the Sound Surveillance System. Engineers began installing thousands of miles of underwater hydrophone cables along the ocean floor, positioning them to take advantage of the long-range sound paths created by the SOFAR channel. Without firing a single shot, the United States had just handed itself a cheat code for ocean surveillance. That discovery changed the way navies approached underwater detection. Instead of relying solely on ships searching nearby waters, they could monitor vast stretches of ocean using the way sound naturally travels underwater. Over time, those early listening stations evolved into large, interconnected surveillance networks capable of tracking submarine activity across entire ocean basins. To understand how that became possible, you first need to understand how sound behaves beneath the surface. The impressive part isn't the listening equipment, it's the ocean itself. Under the right conditions, seawater allows certain sounds to travel far farther than most people would expect. That's why the first step is understanding the sound a submarine makes and how that sound moves through the ocean. Sonar, whether active or passive, is fundamentally a game of shout and listen. In active sonar, a ship sends out a massive pulse of acoustic energy, a sound wave traveling through water. That pulse hits an object, bounces off, and a tiny fraction of that energy returns to the receiver. In passive sonar, the target itself acts as the transmitter, radiating the mechanical noise of its engines, pumps, and propellers into the surrounding fluid. To understand why detecting a submarine at extreme distances should be impossible, we have to build the physics from the ground up. Every sonar system, underwater microphone, and submarine detection network relies on the same fundamental calculation, which is determining how much weaker sound becomes as it travels through the ocean, and that's exactly what the acoustic transmission loss equation does. It accounts for the spreading of the wave and the energy absorbed by seawater, allowing engineers to estimate the sound level at any distance. So let's see where it comes from step by step. We start with our source, a submarine's propeller cavitation, or an engine pump radiating an acoustic power output, which we'll call P0, measured in watts. If the ocean were a uniform, infinite body of water with constant temperature and pressure, that acoustic energy would radiate outward equally in every direction. The power density at a distance r would spread over the expanding surface of a giant sphere. To calculate the acoustic intensity I at a distance r, we divide the initial power by the surface area of that sphere. I of r equals p0 over 4 pi r squared. This gives us the classic 3D spherical spreading law. If we convert this intensity ratio into decibels to measure transmission loss, the math reveals a punishing penalty. TL spherical equals 20 log 10 of r. Every time you double the distance r from the submarine, the sound intensity drops significantly. It drops by a factor of 4. Furthermore, water isn't a vacuum. As a sound wave travels, the water molecules physically vibrate, bumping into one another. Friction converts that mechanical sound energy into heat. This phenomenon is known as acoustic absorption, represented by the attenuation coefficient, alpha. When we add absorption to our spherical transmission equation, we get the total transmission loss for a sound wave in open water. TL equals 20 log 10 of r plus alpha r. This is the sonar engineer's curse. It is one of the most punishing relationships in sensor physics. Because of that logarithmic distance term combined with the linear absorption loss, alpha r, an engine noise radiating at 160 decibels near the submarine should drop below the ambient background noise of the ocean, the sound of waves, rain, and marine life after just 20 or 30 miles. So if the physics of fluid mechanics is doing so much work to suppress the sound, why could Maurice Ewing hear 4 pounds of TNT from 3,000 miles? It comes down to a misleading assumption in our math. The ocean is not an infinite, uniform block of water, and because it is not uniform, sound does not travel in straight lines. Physicists soon realized that sound in water behaves almost identically to light in glass. It is subject to refraction, and if acoustic energy can be refracted, the ocean can be turned into a lens. To understand why, we have to look at an important variable that governs underwater acoustics, the speed of sound in seawater, denoted as c. On land, the speed of sound in air is relatively stable, but in the ocean, the speed of sound is a dynamic, constantly shifting variable driven by 3 physical parameters: temperature, salinity, and pressure or depth. Engineers express this relationship through empirical formulas, the simplest being Medwin's equation. Notice what this equation tells us. 1. As water gets warmer, sound travels faster. 2. As pressure or depth z increases, sound travels faster. If you plot the speed of sound across a cross-section of the ocean, you get a curve known as the sound speed profile, SSP. And this profile creates 3 distinct zones that govern the entire underwater world. First, at the surface, we have the mixed layer. Heated by the sun and churned by winds, this water is warm and relatively uniform. Below the mixed layer lies the thermocline. Here, solar heat can no longer penetrate. The water temperature drops rapidly with depth. Because temperature is falling fast, the 4.6 T term in our equation dominates, and the speed of sound plunges dramatically. Eventually, you reach a depth of around 1,000 meters, about 3,300 feet. Here, the water reaches a permanent, freezing baseline of roughly 2 degrees Celsius. It can't get much colder. From this point down to the seafloor, temperature stays constant, but pressure increases relentlessly. Now, the plus 0.16 Z term takes over. The immense weight of the water compresses the fluid, forcing the speed of sound to climb steadily all the way to the seafloor. If you trace this sound speed profile on a graph, you see a striking boomerang shape. The speed of sound drops to its absolute physical minimum right at the transition zone between the cold thermocline and the high-pressure deep ocean. This depth of minimum velocity is called the SOFAR axis, the sound fixing and ranging axis. Now, why does a minimum velocity layer matter? Because of the fundamental law governing every wave interaction in the universe, Snell's law of refraction. Cosine of theta 1 divided by c1 equals cosine of theta 2 divided by c2. Where theta is the angle of the sound wave relative to the horizontal, and c is the local speed of sound. Snell's law dictates a simple, unyielding physical rule. A sound wave traveling through a medium with varying speeds will always bend toward the region of lower speed. Sound acts like a lazy traveler. It constantly curves toward the cold, slow water. Think about what happens to a submarine cruising right along the SOFAR axis. When the submarine's propeller emits a sound wave angled slightly upward toward the surface, the wave enters warmer water where the sound speed, c, is higher. According to Snell's law, as c increases, the wave's path must bend downward, curving back toward the slow speed axis. When the wave overshoots the axis and travels downward into the deep ocean, it enters a region of massive pressure where c increases again. Snell's law forces the wave to bend upward, curving back toward the slow speed axis once more. The sound wave is trapped. It cannot escape to the surface, and it cannot hit the ocean floor. It is forced into a continuous oscillating sinusoidal wave path, bouncing back and forth along the SOFAR axis without ever touching a physical boundary. And here is where the math breaks the radar equation's curse. Because the sound waves are trapped inside this invisible 2D horizontal channel, they can no longer expand spherically into 3D space. The energy is constrained vertically. The sound spreading collapses from 3D spherical spreading, 4 pi r squared, into 2D cylindrical spreading, 2 pi r h. So let's rework our transmission loss equation for a wave trapped in the SOFAR channel. I of r equals P0 divided by 2 pi RH. Converting this back to decibels, TL cylindrical equals 10 log 10 of R plus AR. Look at that first term. It changed from 20 log 10 R to 10 log 10 R. By confining the wave to a 2D plane, physics has cut the logarithmic rate of signal decay in half. The severe geometric spreading of open water is dramatically reduced. Instead of dying out after 30 miles, a low-frequency sound wave trapped in the SOFAR channel can travel tens of thousands of miles across entire ocean basins, losing only a fraction of its energy. Maurice Ewing's 4 pounds of TNT didn't beat the laws of physics. It simply exploited the fact that sometimes the ocean can act as a giant planet-sized fiber optic cable for sound. As researchers gained a better understanding of the SOFR channel, the U.S. Navy saw an opportunity. Instead of relying entirely on ships to search for submarines, they could leave hydrophone arrays in the ocean and let the water carry the sound to them. That idea became the basis of Project SOSUS. During the Cold War, long lines of underwater hydrophones were installed at strategically chosen locations across the Atlantic and Pacific, where they could monitor the low-frequency sounds that travel long distances through the ocean. When a submarine left port, machinery such as its turbines, pumps, and reduction gears generated low-frequency noise. Some of that sound entered the deep sound channel and propagated for hundreds of miles. The hydrophone arrays recorded those signals and transmitted the data to shore-based processing centers for analysis. By comparing the arrival times and bearings from multiple arrays, analysts could estimate a submarine's position over very large distances. While SOSUS couldn't pinpoint a submarine's exact location on its own, it could narrow the search enough for aircraft and surface ships to investigate further. As long-range acoustic surveillance improved, submarine design evolved alongside it. Engineers worked to reduce machinery noise, isolate vibrations from the hull, and make submarines harder to detect in the first place. If the enemy is listening to the SOFR channel, how does a submarine stay hidden? Method 1. Hiding above the thermocline. Submarines started operating above the thermocline in the surface layer. When a surface ship fires an active sonar pulse downward, that wave hits the steep temperature drop at the thermocline. Because the speed of sound drops so fast at that layer, the thermocline acts almost like a liquid mirror. The sonar waves bounce off the thermocline and reflect back toward the surface, leaving a massive cold water acoustic shadow zone beneath it. A submarine sitting just a few hundred feet below the thermocline can be completely invisible to a surface ship's sonar just 2 miles away. Method 2. Convergence zone bouncing. If a submarine is deep below the SOFR axis, its sound waves shoot downward at a steep angle into the abyss. When those waves hit the extreme pressure of the abyssal plain, 4 or 5 miles down, they experience an intense upward refraction. The deep ocean pressure forces the sound waves to bend sharply toward the surface, focusing all their acoustic energy into a tight, highly concentrated ring on the ocean surface, roughly 30 to 33 nautical miles away. This phenomenon is called a convergence zone. A hunting warship might hear absolutely nothing from a submarine at a distance of 10 miles, 15 miles, or 20 miles. The sub is sitting in a dead zone. But suddenly, at around 30 miles, the submarine signal curves back to the surface and the warship's sonar screen lights up. If the sub moves to 35 miles, the signal vanishes again, only to reappear at the second convergence zone ring at 60 miles. Submarine commanders learn to navigate these concentric rings of sound like a game of blind 3D chess, using the ocean's refraction geometry to hide in the silent gaps between the rings while tracking their enemies on the boundary lines. At the same time, mechanical engineers turn to brute force acoustic damping. If you can't change how sound travels through the water, you have to stop your submarine from making sound in the first place. Engineers began covering submarine hulls with thousands of synthetic rubber tiles called anechoic coating. These tiles are embedded with microscopic air cavities designed to absorb incoming active sonar pulses, converting the acoustic energy into heat before it can bounce back to the enemy. Inside the submarine, massive diesel engines and steam turbines were decoupled from the hull. Instead of bolting machinery directly to the steel frame, entire engine rooms were suspended on massive, shock-absorbing pneumatic raft systems. A vibration originating in a turbine pump is absorbed by the floating raft before it can reach the outer hull and radiate into the sea. Propellers, the biggest source of low-frequency sound, were completely redesigned. When a standard propeller spins rapidly, the pressure drop behind the blades causes the surrounding water to vaporize, creating tiny vacuum bubbles that collapse violently. This process, called cavitation, sounds like pumping gravel, rocks, or marbles through metal pipes, a beacon for SOFAR arrays. To eliminate cavitation, modern stealth submarines abandoned traditional propellers entirely. They moved to pump jet propulsors, shrouded rotor stator systems engineered using advanced computational fluid dynamics. A pump jet pressurizes the fluid before it accelerates it, suppressing cavitation bubbles even at high speeds. Through an enormous effort of mechanical engineering, modern nuclear submarines reduce their acoustic output by over 40 decibels. Because sound intensity is logarithmic, a 40 decibel reduction means a modern Virginia-class or Vanguard-class submarine radiates lesser acoustic energy into the water than its Cold War predecessors. They became so quiet that their machinery noise dropped below the ambient sea state noise of the ocean itself. The SOFAR channel, which had once rendered the ocean transparent, fell silent.